This lesson is going to be on electric fields. All right. To help us understand electric fields better, help us understand point charges better, we draw electric fields. Now, this is a positive point charge. It's in the middle. And let's pretend it's stationary. All right, let's pretend this positive point charge is stationary. Now let's pretend that this sensor on the bottom, this yellow dot, is a positive charge and it can move. What's going to happen if you put this yellow dot anywhere near this stationary positive point charge? Well, what's going to happen is that it's going to start moving away, right? Because they repel each other. So I just put that down. So I just put this down. And what do you guys see? What do you guys notice?
The arrows are moving away.
Yeah, this arrow right here represents the electrostatic force. It's saying that there's a force on this positive charge that's forcing it away. So over time, if we played, right, because this is right now, it's like you're pausing it basically. If we played this, if this was a video, what would happen is that this sensor would just keep moving outward because it's being repelled. That's what these arrows represent. These arrows give you an idea of what would happen if you were to put a positive charge in around this electric field. Now, let's now put a negative point charge here. Let's put a stationary negative point charge over here. And what do you think is gonna, where do you think the sensor will go if I put this sensor anywhere near this negative point charge?
It's gonna go towards the negative.
Yeah, let's put it down. And you're right. It's going to start going towards the negative point charge. Do you guys understand what I'm trying to get at here about electric field lines? Or is there any confusion about what would happen? Right, which is why the arrows point inward. Which is why we draw our electric field lines as pointing towards the negative. Because we're always going to assume that this charge is positive. What would happen if we were to put a positive charge anywhere near this charge in the middle? And I summarize it over here. What's happening? Okay. And I summarize it over here in the Go formative. The electric field lines tell you what would happen if you were to put a positively charged object near a point charge. For example, if you were to put a positively charged object, right, near a positive point charge, it would repel and fly away, which is why the arrows point away. They point away from this positive charge. I look at, if I'm moving this charge around, look at that. All right, so that's really the answer to questions 1 and 2, right? Question 1 should be out. Question 2 should be in. Simple answers, simple answers. All right. Let me just erase this because I did this for my last class. Now, electric fields aren't as simple. They're never that simple. You're never going to get things that simple in real life, right? This is extremely simple. This is like a positive point charge with nothing anywhere else. It gets a little bit more strange if you were to have two positive point charges here now. And you see something peculiar. You see what resembles field lines repelling each other. Because this is what you see now. You see electric field lines just moving away. Well, they kind of curve near the middle, but near the outer edge, they don't really curve all too much. Once you get to the outer edges, they're not really curving. So this is what an electric field would look like for two positive point charges. And so you would draw it over here. Right? You would draw it over here. And you would basically be, and I'll use my mouse to draw it. Right? I'll use my mouse and I'm gonna draw it using my mouse. So you have two positive point charges. Right? And there you have arrows pointing out. Right, they're pointing out. And as you get that's only for the inwards though. That's only for the ones near the middle. As you get to the outer edges, you see them more straight, but near the middle they're kind of curved. And there's a reason for that. Why are they curving? Why are they curving like that? Oh, oh. You can definitely bump into one another. It's actually a much simpler reason. It's literally one word reason. If I were to put, let me just redraw the field line. If I were to put a positive charge anywhere near here, what's going to happen is this object will want to go along this curved path. Neither of these 2 point charges wants this sensor. Neither of them want it. They hate each other. They hate each other and they hate this yellow charge. And so they're going to try to force them away. And so what path will this point charge take? What path will this yellow dot take? Well, it will take the path of this curve. It will follow this curve upward. Or if you're dropping it down here, it'll follow this curve downward. So that's why they curve because they are repelling each other. These lines indicate repulsion. right? You're basically, you don't really want to get near each other. So you're kind of like repelling each other. These lines are repelling each other. It's basically like if, let's say this is positive, this is a positive dot here, right? And this point charge wants to move it that way. But this guy doesn't want it either. So he's starting to push it this way. And because both these point charges are pushing on this object right here, it's going to take a curve-like path upward. Neither of these 2 point charges want this guy. They're both pushing on this object. And what does that path look like? What is the end result when both of these objects are pushing on the sensor? Well, it's just going to take a curved path upward. One more question though, this is unrelated. Why are the lines dimming near the outer edges? Why does it get more dim? What does that signify? Power starts going down? I wouldn't say it like that. Because the electric force is less. Yes. The farther away you get from this object, you feel less force. You feel less electrostatic force. Look at the arrow. This object barely feels anything, but as you get closer and closer and closer, the electrostatic force of repulsion increases. So the electric force, as you get farther away from something, decreases, which makes sense because if that was the case, we'd all start attracting one another. Right? You don't want this. You don't want the distance to be infinite. All right. What do you guys think? So we just did 2, right? We just did 2 of these. We did 2 positive point charges. What do you think 2 negative point charges are going to look like? That would require force. Well, again, as you get closer and closer and closer, the energy required to keep 2 positive charges together requires an infinite amount of force because there's an r squared on the bottom. It's an exponential curve. The force required to keep something together, because in the formula it's kq1 and q2 over r squared. This squared requires a lot of energy for that to happen. But back to the original question. What do you think the electric fields will look like if you had 2 negative charges next to each other? What do you think it's going to look like? It's not a trick question, guys. More attraction, but they're both the same charge. They're both 1 nanocoulomb.
Is it gonna be like curved lines going towards the center?
Yeah, it's literally the same exact thing, except the lines are going inwards now. So it's the same thing, except inward. So instead of lines going inward, You have line. I mean, instead of lines going outward, you have lines going inward now. So draw that for number 4. That's number 4, right? The white things are positive. What do you mean? What do you mean the white things are positive? The white arrows? The white arrows indicate the path a positive charged object would take. The white arrows themselves are not positive, they're just imaginary lines. But the white arrows indicate the path that a positive object would take. If you were to drop a positive object right here, what would happen is that it would slowly curve inward. Would slowly curve inward. Any questions about this, guys? Please raise your hand. All right. All right. Let's move on. Let's move on to question number 5. Hopefully you guys drew it for number 5. It looks like, oh no, number 4. Number 4. I'm sorry. It looks like 11 of you drew something. So hopefully you get it done by 2:00 because I'm doing attendance based on Go Form 2. 11 of you. That's just disappointing. You're breaking my heart. You can't draw right now? I mean, I'm assuming some of you are gonna upload the pictures, right? Some of you will just upload the pictures. Anyway, what's gonna happen when you have a positive point charge and a negative point charge is that, well, the arrows are just gonna start curving towards the electron. I mean, not the electron, the negative charge, right? I like these electric field lines between a positive and negative point charge the most. Your drawings are hideous. My drawings are hideous. Have you seen my handwriting? All right. Anyway, this is kind of what it would look like, right? You have electric field lines and they're curving towards a negative charge. Any questions, guys? Please let me know. Also, electric fields are not magnetic fields. They're two very different things. Electric fields are not magnetic fields. Electric fields are magnetic fields are actually, I mean, they're both real, but they're two completely different things, or a result of two completely different things. That's fine. How can you draw it? It's on the show your work. Just click show your work. So if you click the button show your work, you can draw it. Let's do that's number 5, yeah, but that's number 5.
Like on my old phone, I had this like pen. Like it was like a fine pen. I used to be able to draw on it, but since I got a new phone, it like doesn't come in. It was like a Note 8. It was like the perfect thing to draw on these. I just can't. So it's just horrible.
You should be able to, you can still buy it, I think. I don't know.
Like a pen? Yeah, I might actually do that. But I don't know. Yeah, it might actually work actually.
I'm not sure actually. I wouldn't know. Go back to the drawing. How much I gave you like so much time.
Wait, did you already take attendance for the drawings?
Yeah. If you just did
You
it, I
got me?
took attendance. Yeah.
You got me?
No, I'll check it at 2 o'clock. I'll check it at 2 o'clock.
Okay.
All right, guys. What we're gonna do is I'm gonna stop it here. All right. I know it's like 5 minutes left.
Wait, do we submit? Do we submit it when
No.
we're done? Or no?
It will save it. We'll save automatically.
Oh,
We'll do number 6 tomorrow. I'll excuse you for attendance sake, but I'm not gonna mark you here. Can you mark me here? I didn't do any work. Can you post the link? I don't have it. It's on the classwork. It's on classwork. So just go to Google Classrooms and it's on classwork. You can leave it. It will save for you. You can just leave it. Anyway, guys, I'll see you guys
Wait,
tomorrow.
is there any makeup work we can do?
Yeah, your makeup work is due to work you didn't do, and there are test makeups for your grade.
Oh,
Right.
okay. Oh, that's
I mean, Maz, I had to laugh there. You just said something. I don't know if you realized what you said, but I'll excuse you for attendance, but I'm not marking you here in the attendance. Like, if you get what I mean. I'll excuse you for the overall point grade, but I'm not marking you here for attendance.
Wait, who said that?
No one. Don't worry about it.
Oh, okay. I don't know.
All right. Have a nice day, guys.